In this video, we're going to be going over collisions in Unit 3, Work, Energy, and Power. So what you need to know about collisions is that internal forces do not change momentum, and also momentum is always conserved in collisions if it is in an isolated system. So we can see that in the top row, that for all 5 types of collisions, momentum is conserved. Now below that, we can see kinetic energy is conserved for elastic. Let's actually focus on elastic for a second. So in elastic, we can see kinetic energy is conserved because the change in kinetic energy is 0. Mechanical energy will usually be conserved in elastic collisions. Objects will separate. That means objects won't stick together. The relative speed of the pre versus post collision will be the same or will be reversed, and they will not have the same final velocity. The directions will be reversed after the collision, and energy problems with these type of collisions are rare. There will be minimal deformation and negligible heat, and also negligible sound, and no internal energy. And some examples of this is an atomic collision, an ideal billiard ball, and an ideal spring. Now for inelastic, we see that momentum is conserved, kinetic energy is not conserved, mechanical energy is not conserved, objects do separate, objects don't stick, relative speed pre versus post is going to be smaller, there will not be the same velocity final, and sometimes there'll be a direction reversal. Energy problems are common. There is some heat, some deformation, there is heat, there is sound, and internal energy increases. Some examples of this are a football tackle, a car crash, bouncing, and a clay bounce. Perfectly inelastic. Now so again, momentum is conserved. Kinetic energy is not conserved. This is the max amount of kinetic energy that can be lost from a collision. And mechanical energy is not conserved. Objects do not separate. And objects don't stick or don't separate. Objects do stick. So after this, they stick together, make one combined mass. The relative speed pre versus post is not available for this type. There is the same velocity final because it's moving as one unit afterwards. So when you have one unit, the mass is combined, so it can only have one velocity. One object has one velocity. There is no direction reversal. This type of energy problem is very common. There is a large amount of deformation. There is heat, which is the maximum amount generated. There is sound. There is the maximum amount of increase of internal energy. And some examples of this are a bullet being embedded in a block, a putty stick, and trains coupling together. Now for reverse inelastic, we have momentum conserved, kinetic energy not conserved, mechanical energy not conserved, objects do separate, objects don't stick. The relative speed pre versus post is going to not be available for this. Same VF is not going to be available. Direction reversal will happen. It's common in energy problems. The deformation will be internal only. The heat is there will not be heat converted to kinetic energy. Sound, yes, there is. Internal energy will be a decrease. And some examples of reverse inelastic explosion collisions is a rubber ball hitting the wall and rebounding, a gun firing, and a spring releasing. Now for perfectly inelastic, we have the momentum is conserved, the change in kinetic energy is going to be less than 0, the mechanical energy will not be conserved, the objects will not separate, the objects will stick, the relative speed pre versus post will be 0. The same velocity, yes, it will have the same final velocity. The direction reversal will not be available, and this type of energy problem is very common. There will be a large amount of deformation. Yes, there will be heat. Yes, there will be sound. And yes, there will be an increase in internal energy. Some examples of this is a block on a track lab that you may do in your physics lab, and also a cart plus cart blur lab that you may do in your physics class. Now, let's start with deriving some important equations that you will be using in elastic collisions. Well, first, before we start on that, let's talk about the conservation of momentum. So the conservation of momentum states that the initial momentum is equal to the final momentum, And then we can take the sum of the masses initially and set that equal to the sum of the masses finally. Now, for a two-object system, we have the P initial equal to m1v1 plus m2v2, and then finally we have m1v1 final plus m1 plus m2v2 final. Now, conservation will set those two equal to each other, and that states the same thing as this right here, actually. So this is kind of redundant. So now, if you convert this to kinetic energy, you have this, and then all those 1/2s cancel out. This would be for elastic collisions. So this is true, and there will always be conservation of momentum for all types of collisions, as long as you have an isolated system. Now we can move this here. Yes. So, yes, you have 1/2 v1, v2, m2, yes. Then you multiply everything by 2 to simplify, or you can just cancel out all those 2's. Now, what you want to do is you subtract the right-hand side and you factor. So then you have m1 v1 2 initial minus v1 squared f is equal to m2 v2 f squared minus v2 initial squared. And then we want to factor the squares. So then we have m1 v1 initial minus v1 final, v1 at I plus v1f, that's going to equal to m2 v2f minus v2 initial times v2f plus v2 initial. Now after this, we can divide the momentum equation result. So then we just have m1 v1 initial minus v1 final is equal to m2 v2 final minus v2 initial. And now we can cancel this factor. So then we have just v1, we have v1 initial plus v1 final is equal to v2 initial plus v2 final. So this will be our elastic result. Now from here we can write this as v1 initial minus v2 initial is equal to negative v1 final minus v2 final. And this is our relative speed form. This is an important equation that you should know. Now moving on to inelastic collisions. What changes is the momentum is still conserved, but now the kinetic energy is not conserved. So in order to, the formula that you will usually be using for this type of collision is m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. So still conservation of momentum, just as over there. And we can actually, instead of that, we can just put F. Okay, now after this, there's no second equation because you cannot use kinetic energy for this because there's a change in kinetic energy. So what we can do is write delta K is equal to KF minus K initial. That's going to be less than 0. Now K initial, that's going to be 1/2 m1v1 initial squared plus 1/2 m2v2 initial squared. KF, that's going to be equal to 1/2 m1v1 squared F plus 1/2 m2 v2 squared f. Now for perfectly inelastic collisions, which is when the objects stick, you're going to have the condition that v1f is going to equal to v2f is going to equal to vf. Now, using momentum conservation, m1 v1 initial plus m2 v2 initial is going to equal to m1 plus m2 times vf. Now, if you solve for the final velocity, then you have that vf is equal to m1 v1 initial plus m2 v2 initial divided by m1 plus m2. This is a formula that you must memorize, or you just, well, it's kind of intuitive. You can kind of derive it because you know that this is the total, and then it's just p plus p is equal to p plus just mv. It's p. Remember, p equals mv total, and you remember that one combined mass can only have one velocity. Now, to talk about the kinetic energy that is lost, your initial kinetic energy is going to be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. Now, your final kinetic energy, that's going to be equal to 1/2 m1 plus m2 vf squared. Now, your delta K, you can write that as kf minus K initial is going to be less than 0, and then this is your maximum loss. So the key idea of this type of collision is that the objects, they start together, and then internal energy becomes kinetic energy. And oh, sorry, no, that's for reversed inelastic. So what I meant to say is that, okay, so for reverse inelastic, you can see what happens here is that you have your initial momentum is equal to 0 here, okay? So then you can solve this relationship. Move this down here. We can solve this relationship, and you're going to have m1v1f is equal to negative m2v2f by subtracting m2v2f. So then from here you can write that v1f over v2f is equal to negative m2 over m1. So if you interpret this, what this means is that the lighter object moves faster. Now, if we were to discuss the energy increase, we have delta K is greater than 0 from the energy source of chemical or spring or internal energy. Now, for perfectly inelastic, this is just a perfectly inelastic with one object initially at rest. One object initially at rest. So given that v21 is equal to 0, then we can do m1 v1I is equal to m1 plus m2 vf. Then vf is going to equal to m1 over m1 plus m2 v1 initial. Now after this, we can represent the kinetic energy that is lost as K initial is equal to 1/2 m1 v1 initial squared, and then Kf is going to equal to 1/2 of m1 plus m2 vf squared, and delta K is going to be less than 0.